The purpose of this example is to demonstrate the use of Rugate synthesis option for the design of rugate-type coatings, i.e., coatings with a continuously varying refractive index profile. In the File, Project menu of OptiLayer, open the directory Lec25D26-1. Load into RAM the data files needed to run this exercise. These are the substrate glass, the layer materials silicon dioxide and tantalum pentoxide, the composite material, composition material, silicon dioxide, tantalum pentoxide, the target file single line NF at 520 to 540 nanometers, and the staring design Rugate layer, start for NF. Before starting the design mode, it is recommended to check the contents of the loaded data files. This can be done using the edit command in the corresponding database windows. The substrate and layer materials have non-dispersive refractive indices of 1.52, 1.46, and 2.05. In the Composition Material Setup window, selections in the Materials fields indicate that the composite material is a mixture of tantalum pentoxide and silicon dioxide. The selection in the field Refractive Index Calculations determines the formula used to calculate the refractive index of the composite material. The numbers in the row below indicate the range within which the material percentages can be changed in the starting percentage value. The selection per layer in the change field means that material percentages can be changed independently in all slices of Rugate layer when it is divided into multiple slices. See below. Go to the General Information window and check that the abbreviations L and H are assigned to the SiO2 and Ta2O5 materials, and the abbreviation A is assigned to the composition material SiO2-TO2O5, the target data file, single line NF at 520 to 540 nanometers, defines a high reflection zone from 520 to 540 nanometers, and high transmittance in the spectral ranges from 400 to 515 nanometers, and from 545 to 700 nanometers. In the Design Rugate layer, start for NF. One Rugate layer is specified. C1 in the Number of Layers field. The physical thickness of this layer is 8,000 nanometers. The presence of the material abbreviation A in the material field indicates that this layer will be considered rugate, as this abbreviation corresponds to a composite material. Note that the Rugate layer has not yet been divided into multiple slices. This will be done later. To begin designing of the Rugate notch filter, select the Rugate Synthesis option of the Synthesis menu. Using the Options button at the bottom of the window, ensure that the refinement method is set to the quasi-Newton DLS. Click the Start button to proceed to the selection of the refinement mode, which will be available in the window that opens. There are two modes: parametrization, in which Rugate layer is described by an analytical formula, and table, in which it is divided into multiple slices, each with its own refractive index. The default selection is parametrization, and we will use it. The analytical formula for describing the Rugate layer is selected in the next line rugate-type. We will leave the default choice, apodized sign. A graphical representation of the selected analytical formula of the Rugate layer can be seen at the lower left part of the window. The parameters field is used to set the values for the analytical formula parameters, as well as lower and upper limits for parameters that can be modified by the refinement procedure. Parameters that can be modified are marked in gray in the value column. Even in the analytical parametrization mode, internal calculations are done by dividing the Rugate layer with continuously varying refractive index profile into multiple slices having different refractive indices. The default value for this number in the first line of the parameters field is 100. Let us change this number to 400. The next parameter, alpha 0, sets the mean value of the refractive index of the Rugate layer. Click on its row to access its initial value, as well as lower, min, and upper max limits. We leave the default initial value of 0.5 and set both limits to 0.5 as well. This means we set the mean refractive index equal to the refractive index of the 50% to 50% materials composition and do not allow it being changed by the further refinement of the analytical formula. The next two parameters, delta alpha and lambda/theta, are the main parameters to work with. They determine the oscillations of the sinusoidal refractive index profile. Lambda/theta parameter is the ratio of the period of the sinusoidal oscillations to the total physical thickness of the rugate layer. Note that the smaller this ratio, the more sinusoidal oscillations of the refractive index are contained within the 8,000 nanometer thickness of the rugate layer. Let us start by setting the lambda value. Click on its row to access its initial value, and limit values, min and max. We will leave the limits as the default values and work only with the initial value. Enter 0.02 into the value field. In the upper left part of the window, we will see a sharp decrease in transmittance to the right of the desired high reflection band. Decreasing the number in the value field will shift this transmittance pulsation to the left along the wavelength axis. Selecting a value of 0.0186 provides a better match of the Rugate filter transmittance to the target requirements. The parameter delta alpha controls the width of the high reflection band. This width increases as this parameter is increased and decreases as it is decreased. Let us change the initial value to 0.2. This provides a better match of the target requirements. MF equals 16.02. We will leave all other parameters at their default values. The last four parameters relate to the analytical form of the apodization window, which in our case is a half cosine window. The effect of apodization is clearly visible in the refractive index profile of the Rugate layer in the left part of the window. The construction of the initial analytical formula for the refractive index profile of the Rugate layer is now complete, and we can proceed to the refining of its parameters. Clicking the Run button in the lower left corner of the window starts the refinement procedure. Upon completion, the MF value is reduced from 16.02 to 10.68. The spectral transmittance of the obtained Rugate filter is still unsatisfactory, so we will refine the refractive index profile in tabular form. Click the Start button again and select Table Mode in the Refinement Mode field. The refractive index profile will be automatically converted into a tabular representation with the same number of slices that was specified in the analytical parametrization mode. Note that in the table mode, there is a slider that controls the smoothness of the refractive index profile. Moving the slider to the left increases the variations of the refractive index between slices, while moving it to the right suppresses these variations. It is often useful to start with higher smoothness requirements and then relax them. Let us move the slider one step to the right. Click the Run button to begin the refinement procedure. We will not wait for it to stop. We will click the Stop button when the MF value close to 4.23 is reached. Click the Start button again and move the slider one step to the left, returning it to its original position. Click the Run button. Very soon the MF value of 2.6 is reached. We can repeat the same steps as above, but now we will use an alternative method for controlling the refractive index profile smoothness. Click the Start button. In the Number of Slices field, change 400 to 800 and click the Run button again. Very soon, even lower MF values will be reached. Various combinations of the above control operations can be applied to achieve low MF values and smooth Rugate refractive index profiles. Once you have a satisfactory Rugate design, you can save it to the design database by clicking Save button at the bottom of the starting window, or by loading it to the general information in T and R and phase windows, and then saving it using the Save Data option in the Data menu. The design database contains several designs of notch filters with good spectral characteristics.